Welcome back, everyone. Ready for another deep dive?
Always.
Today, we're going to be looking at thallium.
Thallium. Huh?
Yeah. It's, well, you might recognize it from some crime novels.
Oh, right. The poison.
Exactly.
Huh.
But we're going to see that there's actually way more to thallium than just its, notoriety as a poisoner's tool.
I'm intrigued.
So, to get started with this deep dive, we've got some great sources. We've got some excerpts from the Royal Society of Chemistry's periodic table website.
The RSC. Nice.
We've also got a Wikipedia article on thallium. And this is kind of cool. We've got an AI-generated summary of thallium's applications.
Well, that's interesting. AI summaries are getting pretty good these days.
Yeah, they really are. So let's start with a little history lesson. Thallium was actually discovered fairly recently, back in 1861.
1861. Wow. That's not that long ago, considering.
Right, and what's really fascinating is that two chemists, William Crookes and Claude Auguste Lamy, they both discovered it independently.
No way. At the same time.
Yep.
And get this, they were both using this brand new technique at the time called flame-spectroscopy.
Flame-spectroscopy.
Yeah. So basically, you burn a sample of a material, and then you look at the light it gives off through a prism.
Oh, I see. Each element gives off a unique spectrum of light, like a fingerprint.
Exactly. So Crookes, he was the first one to notice this bright green line in the spectrum.
Green, huh? So that's where the name thallium comes from.
You got it. Thallium comes from the Greek word salos, which means a green shoot or a twig.
It's kind of ironic considering its reputation as a poison.
Right. You'd think they might have gone with something a little more menacing sounding. Haha.
But hey, sometimes appearances can be deceiving, right?
True enough. So Crookes noticed the green spectral line, but Lamy, he actually went a step further.
What did he do?
He managed to actually isolate a small piece of thallium metal.
Wow. So there was kind of a race to be recognized as the discoverer. Yeah, there was definitely some competition there. It just goes to show that, scientific discoveries aren't always clear-cut. There's a human element to it, too.
For sure. And I bet that rivalry probably pushed both of them to work even harder.
Definitely. Now let's talk about some of the properties of thallium. It's got this, what I like to call a dual personality because of its two main oxidation states.
Oxidation states. Can you explain that a bit? Not all of us are chemists here.
Oh, right, sure. So think of oxidation states as like different costumes an element can wear. They kind of determine how an element interacts with other elements.
Okay, I kind of get it. So what are thallium's different costumes?
Well, it's got a +1 state and a +3 state.
+1 and +3, okay.
In its +3 state, thallium acts kind of like its buddies in groupthink 10 of the periodic table, like boron and aluminum.
Right, the boron group.
But when it's in its +1 state, things get interesting. It's like it decides to go rogue and act more like an alkali metal. Specifically, it starts mimicking potassium.
Mimicking potassium.
Yeah, it tries to be like potassium. And that's actually where things get a little dangerous.
Ah, now we're getting to the poison part.
Yeah, exactly. Remember that Agatha Christie novel we mentioned, The Pale Horse?
Oh, yeah.
Well, that book actually features thallium poisoning as a key plot point.
And she described the symptoms pretty accurately, didn't she?
She did. It's actually kind of creepy how well she understood the effects of thallium poisoning. But, some people think that by writing about it so accurately, she actually helped raise awareness about how dangerous it is.
That's interesting. It's like her fiction might have actually saved lives.
Yeah, it's kind of wild to think about. Okay, so we know it's dangerous, but thallium is also super rare. It's not just lying around everywhere.
So where do you even find it?
Well, mostly you find it as a byproduct of refining those heavy metal sulfide ores.
Oh, so it's kind of like a hidden treasure.
Yeah, you could say that. And even the minerals where it's found have these really complex names, like Cooksite.
Crooksite for William Crookes, I bet.
Yep. And then there's Hutchinsonite and Laurendite.
Those are some mouthful names.
Right. It's like they knew this element was going to be a bit of a mystery. I read that that French chemist Jean-Baptiste Dumas, he actually called thallium the duck-billed platypus of metals.
The duck-billed platypus of metals. That's a weird comparison. Why did he say that?
Well, think about it. The platypus is this, totally unique creature. It's got features of both mammals and birds, right?
Yeah, it's kind of an oddball.
Exactly. And thallium, it's kind of the same way. It's got those two different oxidation states, so it can act like a metal from group 13 or like an alkali metal. It's unpredictable.
So it's a rare bird, or should we say a rare platypus, of the periodic table.
Uh-huh, exactly.
Okay.
Now, enough about its poisonous past. Let's move on to something a little more upbeat. Thallium has some really cool applications, even though we don't use it for rat poison anymore, thankfully.
Oh, yeah. I read that it's used in electronics, optics, and even glass making.
It's true. It's super versatile. So let's start with its use in electronics. Have you ever heard of photoresistors or bolometers?
I can't say that I have.
Okay, well, photoresistors are used to control electrical circuits based on how much light is hitting them.
Oh, interesting. So like a light sensor.
Yeah,
Huh.
exactly. And then bolometers, they're used to measure infrared radiation.
Infrared, huh?
Ugh,
So that's heat.
you got it. So what makes thallium so special for these devices is that its electrical conductivity changes when it's exposed to infrared light.
Oh, I see. So it can detect those changes in infrared light.
Yep. Pretty neat, right?
Definitely. What about its use in optics? I saw something about KRS-5. What in the world is that?
KRS-5. I know, it sounds like some kind of secret code, right?
It does. Is it some kind of spy gadget?
Haha, not quite. KRS-5 is actually the trade name for a special type of crystal. It's made from thallium bromide and iodide.
Thallium bromide and iodide.
Yeah, it's a mouthful. But the important thing is that these crystals are amazing at transmitting infrared wavelengths. So they're really useful for all sorts of infrared optics applications.
Wow, so it's like a superpower for anything involving infrared light.
Pretty much. Now let's talk about glass. You might not think that thallium and glass go together, but
I mean, I don't usually associate praisen with something I drink out of.
fair enough. But when you combine thallium with certain elements like sulfur, selenium, or arsenic, something amazing happens.
What's up?
You can create this special type of glass that has a really high refractive index. That means it bends light in a very specific way.
Huh, okay.
And what's even more interesting is that this glass has a really low melting point. We're talking somewhere between 125 and 150 degrees Celsius.
Wait, that's way lower than normal glass.
Right. And because it melts at such a low temperature and it's also super durable and water resistant, it's perfect for making electronic parts and other special products.
So it's like a super glass.
Kind of. It allows you to do things with glass that you just couldn't do with regular glass.
All right.
Now, I know we've been talking about all these cool applications of thallium, but we can't forget that it's still a potentially hazardous element.
Right.
I mean, we don't use it in rat poison anymore, but there's still some environmental concerns we got to think about. The EPA, they've identified a few sources of thallium pollution, and some of them are kind of surprising.
Like what?
Well, cement factories, for one.
Cement factories.
Really?
Yeah.
And also coal-burning power plants.
That makes sense, I guess.
And get this, even metal sewers can contribute to thallium pollution.
Wow, I wouldn't have thought of that.
Plus, there's the issue of leaching from ore processing operations.
Leaching.
Yeah, so basically thallium can seep out from the ores during processing and contaminate water sources. It's a serious issue.
So even though we've moved on from using it as a poison, we still need to be really careful about how we handle thallium and dispose of it properly. It's a good reminder that even when we find beneficial uses for an element, we can't ignore its potential risks.
You're absolutely right. Now, before we jump into thallium's role in nuclear medicine and the exciting world of high-temperature superconductors, let's take a quick breather and think about what we've learned so far. It's pretty incredible, right?
Totally. It just blows my mind how one element can have such a diverse range of properties and applications.
Me too. And we're just getting started. Thallium, huh? What a wild ride so far. But wait, there's more.
More. There's more than electronics, optics, and special glass.
Oh yeah, buckle up. Remember when we talked about thallium's role in nuclear medicine?
Vaguely.
Okay, well get this. There's a specific radioisotope of thallium, thallium-201.
Thallium-201.
And this stuff, it's like a superhero for
A
cardiologists.
superhero. How so?
Well, it plays a crucial role in nuclear cardiac stress tests.
Stress tests, like on a treadmill.
Yep. But these are special stress tests. They help doctors actually see the blood flow to your heart muscle.
Wow, that sounds intense. How does that even work?
So basically, they inject a tiny bit of thallium-201 into your bloodstream.
Into your blood.
Yeah. And because thallium is so good at mimicking potassium,
Right, the whole potassium mimicking thing.
well, your heart muscle cells, they basically gobble up the thallium-201 thinking it's potassium.
Icky.
Then they use these special cameras that can detect the radiation coming from the thallium-201.
Radiation.
Yeah, it's a very safe amount, don't worry. But the cameras use that radiation to create images of your heart.
So they can actually see where the blood is flowing.
Exactly. They can see if there are any areas of the heart that aren't getting enough blood.
That's amazing.
Yeah.
So in a way, thallium's potassium mimicking thing which makes it so dangerous as a poison,
Mm,
is actually what makes it so useful in this case.
you got it. It's all about perspective, right?
Mm.
Understanding how an element behaves and then using that knowledge for good.
It's like turning a villain into a hero.
Exactly. Now, ready for something even more mind-blowing?
Bring it on.
High-temperature superconductivity. Ever heard of it?
I think so. Something about electricity flowing with no resistance.
Yep. It's basically a superhighway for electrons. They can zoom around without any obstacles, so there's no energy loss.
Sounds pretty efficient.
Efficient is an understatement. Now, here's the thing. Regular superconductors, they gotta be super cold to work, like close to absolute zero.
Brr. That's not very practical.
Nope. But high-temperature superconductors, well, they can operate at much higher temperatures, above the boiling point of liquid nitrogen even.
Liquid nitrogen, so still pretty cold, but not absolute zero cold.
Right. And that's a game changer because it means we can actually start thinking about real-world applications for this stuff.
So where does thallium fit into all of this?
Well, back in 1988, scientists made a big discovery, a thallium-containing compound that acts as a high-temperature superconductor.
No way. What's it called?
Thallium, barium, calcium, copper oxide, if you can believe it.
Try saying that 3 times fast.
Haha, I know, right?
Hey.
But the important thing is that this compound can achieve superconductivity at those more accessible higher temperatures.
Because of the thallium.
Partly, it's got to do with the unique structure of the compound and how the electrons interact within it. It's pretty complicated stuff.
So what kind of real-world applications are we talking about here? Flying cars, teleportation.
Haha, not quite yet. But imagine MRI machines that can produce even clearer images, leading to more accurate diagnoses. Or energy storage systems that are so efficient, they could power entire cities without any waste.
Wow, that's incredible.
And what about high-speed trains that levitate using magnets thanks to superconductivity? Faster travel, less energy consumption, it's a win-win.
Okay, now you're talking. So thallium, this poison, is actually helping us move towards a more sustainable future.
It's crazy, right? It just shows you how important it is to really understand the elements around us. You never know what amazing things they might be capable of.
Mind blown.
Now, remember that AI-generated summary we mentioned earlier?
The one about thallium's applications?
Yeah, well, it mentioned something I found super intriguing. Thallium in imitation jewelry.
Thallium in jewelry? Really?
I know, right? It's not something you'd expect. Unfortunately, the summary didn't go into much detail, but it makes you wonder, how exactly are they using it?
Maybe it can mimic the look of precious metals. Or maybe it adds some cool colors to glass.
Those are good guesses. It definitely makes you wonder if there are any vintage costume jewelry pieces out there with a hidden dose of thallium. Ha. Hopefully whoever was making them knew what they were doing and took the proper precautions.
Yeah, that's a good point. Even in something as seemingly harmless as jewelry, you gotta be aware of the potential risks.
Absolutely. It all comes back to understanding the full spectrum of an element, both the good and the bad. And I think thallium is a perfect example of that.
Totally. It's a powerful reminder that we need to be responsible with the elements we use, even the ones we think we understand.
Well said. Now, before we wrap up our deep dive into the fascinating world of thallium, I want to touch on something you said earlier.
What?
You mentioned the importance of understanding the full spectrum of an element, both its benefits and its risks. And I think thallium is a perfect illustration of that idea. It's a complex element with a complicated history, but it also has the potential to do some truly remarkable things.
I couldn't agree more. It's a story of caution and possibility, all wrapped up in one tiny element on the periodic table.
It's a story that reminds us that scientific exploration comes with responsibilities. As we delve deeper into the mysteries of the elements and discover new ways to harness their power, we need to be mindful of the potential impact on human health and the environment.
Absolutely. It's a delicate balance, but one that we can't afford to ignore if we want to create a more sustainable future.
It's amazing, isn't it, how one tiny element can have such a big impact?
It really is. Thallium, I mean, who knew?
Right. From poison to, like, the future of technology.
Yeah, what a story.
And, I think it's a story that's still being written.
Oh, absolutely. We've only just scratched the surface.
Exactly. So to everyone listening out there, keep exploring, keep asking questions, keep being curious.
The periodic table is like, it's full of surprises just waiting to be discovered.
Maybe one of you listening will be the one to make the next big thallium breakthrough. But until then, thanks for joining us for this deep dive into the world of thallium. We'll see you next time.